All right, so we're going to talk about inverse functions today. This is section 1.7, so you definitely want to fill in your notes with this. To begin with, we want to talk about a bit of a definition. So if you notice, I've got some information here about what one-to-one means. And if you notice, I've written here that it explains that each y value corresponds to only one x value. So think visually about what that means, and then we're going to look at some examples. So visually, if we were to draw that mapping, you would notice that the mapping has to go from one x value to a single y value in each particular case. So that's what the mapping would look like. So in order to check visually on a graph, we want to do the horizontal line test, and that helps us determine whether or not a function is one-to-one. So I want you to think about the fact that if we do the horizontal line test, what that's really telling us is that our graph cannot be an even function. So I want you to think about the symmetry involved there. If it's an even function, we know it's symmetric with respect to the y-axis. So that would imply corresponding y values. So for it to be one-to-one, it cannot be an even function. So I have some examples here of functions here, and the lines are already drawn in there for you. We're doing the horizontal line test to check for one-to-one, so this is definitely not. There's only one place you could hit points on this graph if you're doing horizontal lines, so yes, this is one-to-one. For this particular graph, this is definitely an even function with our symmetry, so that's why this is a no. And same thing here, we definitely have our symmetry. This is an even function, so the answer is that is not one-to-one. So remember what we've learned about inverse functions. I've kind of got some special notes here for you. If you recall, to check or verify if functions are inverses of each other, we have to check and verify both directions. We have to find f of f inverse of x and f inverse of f of x, and our answer should always be x, which remember is our identity. A couple other reminders, and that is if we know the domain for a function f, if our domain is x, and then we have our corresponding y values, which would be written as f of x, then remember for our inverse function, these switch. So the domain for f becomes our range for our f inverse, and what would be our range for our original graph, our original function, becomes our domain. So this would be that the domain for f inverse is our y, or our f of x. Okay, and then remember the graphs. If we're drawing visually and looking visually at a graph, the graphs are symmetric with respect to the line y is equal to x, which remember is this graph that goes right along our diagonal. And we'll look at that here shortly. So remember, to determine if functions are inverses of each other or are not, we have to do f of f inverse, and we should get x as our answer, and f inverse of f, and we should also get x. We've got to plug in. So if we plug, in this case, I've written them as big Y and little y. If we decide to plug in and do 2 times that quantity, that function, minus 5, so I'm plugging into this function, and I'm going to plug this in. I'm putting in 1/2 x plus 5. So if I clean this up, I should just get x, and let's see what we get. We get x plus 10 minus 5, which is equal to x plus 5. So I do not get x. So technically we should check both directions, but since we already see that this is not working, there's no point in checking the other direction. If we had plugged in the other way to begin with, it would be 1/2 times that big whole quantity plus 5, and we would plug in this 2x minus 5 into that spot. So we get x minus 5 halves plus 5, which is definitely not equal to just x either. So we know that they are definitely not inverses of each other. Let's try this second one though. So let's plug in, let's do 4 times that quantity minus 3. And I know it's everybody's favorite thing in the world. We've got fractions here. They are manageable, I promise. So when we distribute here, we get x plus 3 and then minus 3. So we do get x when we do this, the composition of functions that direction. So now we've got to go the other way. So 1/4 times quantity plus 3/4. And I'm going to plug this in. So I get 4x minus 3. So when I distribute here, I get x minus 3/4 plus 3/4. I do get x for my final answer. So yes, these two are inverses of each other. If you recall, the next type of problem is that we might be asked just to find what the inverse is. And so in this case, remember, we switch our x and y. So our original problem says this. I'm rewriting this h of x with y in it because now I want to switch and rewrite and write this as x. I'm going to switch back and forth in colors, is equal to 3y, because I want to stress the fact that we're switching that x and y. And now we're going to solve for y. So to solve for y, I need to subtract the 4 from both sides. And I've got to divide by that 3 on both sides. So I get 1/3 x minus 4/3. Lastly, let's talk about how we can find the inverse of a graph if we're just given the visual graph. So remember that the inverse functions are symmetric with respect to the line y equals x. So that's why I've drawn in that highlighted line for you. There are a couple of ways of going about dealing with this. For some people, they are really good at visually drawing from this line and drawing the symmetry. For others, it's helpful to pick out specific points like this -1, 1. That is that point. So what that means is that for the inverse would be at 1, -1. The x and y value will switch. So that means we need to put a point here. I'm also seeing this point 1, 1. That's going to be the same for both graphs. And then let's pick one more point here just to kind of help us get the shape of that line there. This point on the original graph is at 2, 4. So let's switch our x and y and let's graph a point at 4, 2. And that's going to help us draw this part of the graph as well. So this graph is going to go that direction. And then to do this, maybe we should do one more point here. Maybe that -4, -2. So let's switch our x and y and go to -2, -4 and put that point in just to help us get what that shape's going to look like. And I didn't draw that very straight. But if you turn your paper and tilt the paper so that your your symmetry line here is going straight up and down, you can visually see the symmetry involved. So let's try the same thing with this last one. We definitely want this point here, and actually we can kind of visualize this and say, okay, this point clearly has to go here. Let's figure out what the coordinates are of that point. That is at 3, 7. So let's graph at we got to kind of visualize where 7, 3 would be. So 4, 5, 6, 7, 1, 2, 3. Our graph's going to go about like that. And then I see this point -2, 0. So let's graph the point 0, -2 to help us get a good idea of where this is going. And once again, you can see visually, if you turn your paper, you can see the symmetry, the fold line, right? All right, hope this helps. Please make sure you let me know if you've got questions on any of this.